everybody, welcome back. So let's continue with this idea of the photon. If you recall, you see that formula boxed up there. The energy of the photon is hf or hc over the free space wavelength, and we can use that combination of hc, we can evaluate it I should say, and use 1243 eV nanometer over the free space wavelength to get the energy of the photon. Okay, so what I want to do now in this video is let's talk about how the energy is actually being delivered in terms of the rate of energy delivery, the power. So let me scroll down here and get some more space. So the power, remember, so what I'm envisioning is, right, there's an emitter here of light, and it's delivering electromagnetic radiation. There's energy in that radiation, so the rate of energy delivery, the rate of the energy is being emitted is the power, right? So in the photon model, this guy is spitting out a stream of photons. And we're going to consider just one frequency. So we're only focusing on one frequency. Okay, so if this is emitting power at all different frequencies, fine, but we're just going to evaluate how to find the power at one frequency. Okay, now, remember, in the classical or wave theory of light, this source is emitting this continuous electromagnetic wave, right? It's traveling like that. Think of that picture that it's in the summary notes, right? That we've looked at it in a couple different videos of that linearly polarized cosine or sine harmonic electromagnetic wave. Okay, so the power delivered, P, right, is energy per time. Remember the the SI units, right? Energy, SI unit is joule, time is second. So power is joule per second, which is a what? A what? Yes, a watt. Okay, so a W. So again, I'm putting my units in square brackets here. Okay. So in the classical wave theory, the energy is going to depend on the amplitude of the wave, right? And then the power is going to depend on that amplitude and the frequency and the speed of the wave, okay? The frequency, because the higher the frequency, the more energy that's going to be carried, right, per time, because you're getting more oscillations per time. And the speed, because of the speed of the energy delivery from one point to another point. And then again, the amplitude, because that's going to give you the amplitude is going to characterize how big the fields can be and the energy stored in the field. For the photon, the energy is only dependent on the frequency. Okay, only dependent on the frequency. So the power is going to depend on the frequency of the light, right? Now, it's got to depend on something else, though, right? It can't just be the frequency. Well, let's think about it. So energy per time. The energy is going to be carried by photons. All the photons at a fixed frequency are going to have the same energy, right? HF, or HC over lambda naught. So at one frequency, take the energy of a photon. Okay, but the number of photons being emitted per time, that's the other critical factor. So what I'm going to do is I'm going to multiply this by, I'm going to symbolize this by R sub pH. I'm going to call that the photon rate. Okay, E sub pH is the energy of the photon. R sub pH is the photon rate. This is the number of photons being emitted per time, per unit time. So this is the number of photons per time. So, units might be number per second, for instance, for using SI. Okay? So the more photons per second that come out of this, the more output power. Right? That makes sense. The actual energy is being lumped in equal amounts at one frequency. So the way you get more energy per time is you just emit more lumps per time. Okay. It's analogous. Sometimes I make the analogy of if I'm throwing money towards you, cash towards you, but I can only throw quarters at you. So how do I get more money to you per time? I just have to throw more quarters per time at you. Okay, so that's the idea. All right, so this is how we're going to formulate power delivery in the photon model. So you should know how to use this equation. Okay. All right, now there's the power. The next thing I want to do is I want to, again, emphasize more the photon as a particle. When we say particle in physics, that brings us back to mechanics. We think of a collection of mass as a particle, right? So particles have kinetic energies, right, of 1/2 mv squared. They have momentum, right? So I'll call this a matter particle. This is just like something made out of matter. We know how to handle this. There is a kinetic energy. So the way you find the energy of a particle, because of its motion, is, I'm going to use big K's, you take 1/2 mv squared, right? The linear momentum, right? You guys remember how to find the momentum of a particle? We use little p for momentum. It's going to be mv, right? This is a vector equation, but let's just consider it traveling in one dimension. So I'll take the vector arrow off. That's how you do that, right? Well, we can treat the photon as a particle because light does carry momentum. We didn't discuss this with the wave model, but even in the wave model, light does carry a momentum, right? It can transfer momentum. When light hits a surface, energy is exchanged because energy is being carried in the wave. So there is transfer of momentum. Now, for typical light sources, right, it's not a huge transfer of momentum. So if you go into a dark room and hit the wall switch, turn on the lights, you don't stagger back when the radiation hits you. But there is a very small transfer of momentum to your surface atoms and molecules. In fact, that's the basis for light sailing. You may have read about NASA actually looking at using huge thin metal sails and using light to sail through space. Sometimes that's referred to as radiation pressure. That's really just the change in momentum that comes about when energy is exchanged. Light sailing is often depicted in science fiction movies, like Star Wars, for instance. Okay, so that's not a radical idea. That idea of momentum didn't come about just when the photon model was developed. In fact, to formulate the momentum, we're going to borrow from classical wave theory. But let's talk about the photon now, okay, as a particle, because it does have characteristics of a particle in that it carries an energy and a momentum. Now, how do you find the analogous kinetic energy of a photon? Well, we normally just call that the energy of the photon, right? So we just write that as, we know how to do that, HF or HC over lambda, or 1243 eV nanometer over lambda naught. Here's something new though, right? How do we find the momentum of the photon? So this is what I want to focus on right now. Well, again, as I said, we borrow from classical wave theory. And the way you would do this in wave theory is you would find the average energy carried by the light wave and divide by the speed. And I'm assuming this is traveling in free space when I write this, okay? So you take the average energy and divide by c. I'm not going to derive that equation. That would take some time. But that's from classical wave theory. Well, so all we do to update this is we say, well, this is the energy of a photon. So we're talking about not a classical wave, electromagnetic wave, but this quantum of light energy, the photon. So here's a formula. This is how you find the momentum of a photon. take the energy of the photon and divide by c. Okay? And this is a fine formula. In fact, I'll say more about that in a sec, but you can, if you want, replace the energy of the photon by this above formula. See that hc over lambda naught? And you can also write this as Planck's constant over the free space wavelength. That's another way you can do that. Okay, so they're equivalent. Now let's talk about units when you go to do this momentum. And let me put a box around this, okay, because that's a formula. And the important formulas are in the summary notes. In fact, I promise I'll go there and show you. I think I promised I would do that in the last video, and I didn't, but I'll show you now that we've developed all these formulas. Let's talk about momentum units, okay? MOM units, right? Momentum units. Okay, so we know SI, you guys remember, right? Just think of MV, that's kilogram times meter per second, which I sort of like writing it as a Newton times a second. I like that, because you remember a Newton is a kilogram meter per second squared. Okay, but that's the SI, okay? However, it is common with photons to just write it as number of EV per C. You don't even put in the value of C, okay? You evaluate the photon energy in EV, and then you just say the momentum is so many EV per C. Now you can convert to SI units if you have to, but it's common just to leave it like that. Let's do an example, and I'll show you. We'll do an example where we find, we use power, the idea of power and momentum. And in fact, let me go to the summary notes right now and show you the example we're going to do. So here are the summary notes for photons. Whoops, right here, right? Here's the energy of a photon. Okay, there you go, right there. We've talked about that. And then if I go to the next page, here's the formula we just developed for the power, the emitted power, right? Energy of the photon times photon rate. And here's the momentum of the photon, the momentum equation. Here's the example I want to do right here. So we're going to consider a helium neon. Oh my gosh. I have looked at this. I must have looked at this 100 times, right? And I just now looking at this. See that? Oh my goodness. I'm so disappointed in myself. Anyway, that's supposed to be laser. And I'll fix it. So if you haven't downloaded this yet or looked at it, I'll fix it and it'll say laser. But I am not going to remake the video and correct that. Anyway, that's a laser. Okay, so a helium neon laser is a common laser. We have a couple of them, more than a couple in the department, and I often do demos with them. It's a gas laser. So the one we have emits about, the ones we typically use, emit around 7 milliwatts of power. Okay, now the wavelength of the helium neon laser, the main wavelength, where they're usually tuned to, is a red wavelength of 632.8 nanometers. Okay, that's the free space wavelength. So we're going to find the energy of a photon, the number of photons leaving the laser each second, and the momentum of a photon. Oh, look here, I got it spelled correctly. Okay. All right, so let me go back to our notepad and we'll write this down. So I'm going to consider my helium neon laser. I know that, so this is an example. I know that the output power, let me confuse that with momentum. This is uppercase P is 7 milliwatts. And I know that the free space wavelength, which is going to be the wavelength in air, is 632.8 nanometers. Okay, so the first thing we're going to do is we're going to find the energy of a photon. All right, so in this picture, right, here's my laser, and it's spitting out this stream of photons in this beam, okay? All right, so the energy of one of those photons is going to be HC over HF or HC over lambda naught, but I'm going to go straight to my 1243 EV nanometer combination, and I'm going to put the free space wavelength in nanometers. It was given to me in nanometers, which is really convenient. And if I just punch that in the old calculator, I'm going to get 1.96 eV. And if nobody asks me for joules, I don't need to convert that. I can just give it, right? Unless somebody says, no, I want that in joules. Okay, so let's leave it like that. Let's go to B. We're supposed to find the photon rate, right? So what is the R sub pH? What's the number of photons per time being emitted by this laser? Well, that's going to be related to the power. Remember, the power is the energy of a photon times the photon rate. So all I have to do, it seems, is take the power and divide by the energy of the photon. Okay, so I'm going to put in 7 milliwatts. 7 times 10 to the minus 3 watts. And I'll divide by the energy of the photon, 1.96 eV. Uh-oh, anybody see a problem? I see a problem. If we just calculate that, we're going to get the wrong value because the watt, remember, in this watt, this is an SI unit, this is a joule second. We have an EV down here. We need to either convert the joule up here to EV or the EV down here to joule. See, should have calculated this photon energy in joules, but nobody told you to. Yeah, but look, we have to do that down here. Well, that's true, but it's not too late. Look, all I have to do is say, okay, I'm going to convert this 1.6 times 10 to the minus 19 joules per EV. Okay, if I'd done that up here, I would have gotten this value right here. See, I gave it to you in joules in A, even though I didn't explicitly ask for it. 3.13 times 10 to the minus 19 joules. Okay, but that's okay. We'll do the conversion here. You punch this in your calculator, and you're going to get about 2.2 times 10 to the 16. And that would be photons per second, right? Because we have seconds left over. Oh, look right here. I made a mistake too. I think I said it correctly, but I wrote it wrong. This is joule per second. So I was doing a quick unit check, and I'm like, wait, I have a second up there. Maybe I pronounced it, I said it wrong too, but this watt is joule per second, guys. Sorry. Okay. So there it is. Yes, that's a lot of photons. Yeah, for typical powers, it's going to be tons of photons. Well, that's not a good thing to say, because the photons actually don't have a mass. Okay? There's going to be many photons. Okay? All right. I was just going to double check. Yes, that's the answer that I got. See, right there. All right, then the last thing we're supposed to find out is what's the momentum of a single photon. Okay, so this is lowercase p. Well, the one formula we have that we can use is we take the energy of the photon divided by c. See, so as I was talking about earlier, what you could do is just say, okay, the energy of one of these red photons is 1.96 eV. And then I just say, I divide by c, and you're done. So you say, oh yeah, the momentum of that red photon is 1.96 eV per c. Okay? But if somebody says, yes, but what is that with SI units? Okay, so one thing you could do is you could say, okay, I could take the 1.96 eV, right? And it's really just substitution of values and conversion. 1.96 eV times 1.6 times 10 to the minus 19 joules per eV. And then I'm supposed to divide by C. So put in the value of C using SI units, 3 times 10 to the 8 meters per second. See, now I'm going to have all SI units, so this is going to be kilogram meter per second or Newton seconds. And that gives you around 1.04 times 10 to the minus 27 kilogram meters per second or Newton times second. Okay. And another thing you could do, and you can check this, I said that another way to calculate momentum is to take Planck's constant over the free space wavelength. So I'll let you check that if you put in 6.63 times 10 to the minus 34 joule seconds divided by 632.8. Now I have to convert the nanometers to meters because I need all SI units. So this is 10 to the minus 9 meters. That should give you 1.04 times 10 to the minus 27. Okay? All right. So these are the types of calculations you should be able to do for photons. But now we have this idea of the photon sort of fleshed out more as a particle. It carries an energy and a momentum. Even though it's not made out of matter, it's pure energy. Okay? Sort of a weird concept, I know. All right. I will see you in the next video where we're going to talk about another phenomenon, the photoelectric effect, where the photon model of light explains things that people observed and the wave model did not. Okay, bye-bye.